Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 45 of our machines subject, that is starting of induction motor. So we have discussed like the dynamic parameters, like what happens when the motor is rotating, if I suddenly reduce the torque or suddenly increase the torque, and also we have discussed about testing of induction motors. Now few topics are left, like starting, speed control and braking. These three topics are left and few theoretical topics like harmonics also are left. Okay, so we will discuss about those. Today we will mainly discuss about starting. So again, if you remember, for those students who have not studied DC machines, because instrumentation students will be there, what happens in starting, we can understand with this equivalent circuit. In starting, what do we know? In starting we know that my motor is just at rest. It will, the speed will just increase. So as soon as I will turn the fan, switch of the fan, the fan will start to rotate. Initially the speed was 0. So initially what is the slip? Initially the starting slip, right, is starting will be equals to what? It will be simply 1, because nr is 0. If nr is 0, the rotor speed is 0. That means ns minus nr is ns. Sorry, it is, yeah, ns. So ns divided by ns will be 1 only. So starting slip will be 1 only. Okay, so the starting slip will be 1. Starting slip will be 1. Now if starting slip is 1, that means what? That means this is gone, right? This is gone. So if this is gone, then what will happen? Then what will be the starting current? So starting current, right, will be equals to, let me write this E2 dash divided by, like I have referred everything to the secondary now, that's why it is E2 dash divided by the stator resistance. I've roughly said that I have just changed this, I have converted this into the rotor side, because roughly the current will be same, very less current will flow through here. That is my approximation. Okay, so R1 plus, although that approximation is not completely correct, but we can do it because the stator resistance will be very low, plus this will be whole squared plus x1 plus x2 whole square, right? So this will be equals to basically my starting current. Now what I can say, what I can comment is that roughly I can neglect the stator resistance as it is very low value. Okay, if I neglect the stator resistance and reactance, roughly this will be E2 divided by under root R2 whole square plus x2 whole square. And let me take few numbers so that we can understand the thing, right? Let me take that E2 dash, let's assume, is equals to 100 volts. My R2 dash is equals to 0.1 ohms. My x2 dash equals to 0.2 ohms, right? So if I calculate the starting current, like I just want to take up few numbers, let me calculate the starting current. So this will be 0.1 whole square plus 0.2 whole square under root 0.223 and into 100. So it comes out to be very high value, 447, right? Something 447 amperes. Okay, now let me take both of them same only, it will be easier for us to calculate. So this will be basically 0.1 whole square plus 0.1 whole square whole under root into 100. So like, are you able to observe what amount of current we are getting? Like this is huge, right? 700 amperes. And in normal condition, what will happen? In normal condition, right, the rotor speed will increase. So if rotor speed increases, the slip also will reduce, right? Because slip is ns minus nr divided by ns. So rotor speed increases, slip will reduce. So if slip reduces, what will happen? If slip reduces, the basically the starting current, you will see the current, full load current will reduce. We can calculate that full load current. So if I want to calculate that full load current, right, I full load, okay, here I have taken few values. Yeah, both of, okay, I have taken both of them to be same only. E2 dash, let me take 100, otherwise it will be some kilo amps of current, that will be too high. So I full load will be equals to E2 dash. Now this time slip is there. If slip is there, right, now I cannot simply neglect this resistance. Now what will be the overall resistance? R2 dash plus R2 dash into 1 by S minus R2 dash. So R2 dash will be cancelled. R2 dash divided by S. So basically this will be under root R2 dash divided by S whole square plus X2 dash. So what is E2 dash? E2 dash is 100 again. Remember what is R2 dash? R2 dash is 0.1 divided by SFL, right? Slip at full load. Full load slip is 0.05. So 0.05, roughly it is 2 ohms, and this is 0.1. This will not change obviously, whole square. Okay. So this value will be 0.1 divided by 0.05 whole square, and 0.1 square can be ignored, so it will be 2 only. So this comes out to a 50 amperes, right? So the ratio of the starting current and the full load current, if you see, is what it is coming out to be 707.1 divided by 50, 14, right? So basically what I can say is the starting current is very high compared to full load current. How can I understand this intuitively? So intuitively, initially the motor is at rest. If the motor is at rest, there is rotating magnetic field. Now the rotating magnetic field is cutting the conductors in the rotor at a very high frequency because the motor is at rest. So the rotating magnetic field is rotating at a very fast speed. So relative speed is still ns. So more flux is getting cut. So more current will be generated on the rotor side. That's why we have higher current, to understand this intuitively. Okay. So of course this is not normal, right? Normally we have rated our motor to operate in 50 amperes of current, but it is taking like huge amount of current, 700 amperes, whenever initially the motor is starting. So initially, if you remember, whenever you start a motor, suddenly the lights, all those things suddenly turn off. So there is bit of voltage drop because it takes huge current from the supply. That's why suddenly you will see lights getting dim, right, when you just start the motor, because it is taking huge amount of current. So of course it is not desirable condition. It is not desirable condition. Our motor may also get damaged. Our like windings and other equipments can get damaged through this, right? So what we'll do, we will add a starter. The starter will basically limit the current, and huge, like it will limit the current by adding few resistance or by other means, so that huge current does not flow through the motor. Okay, so that is what is written over here. So why special starting techniques are required? At instant of starting, the rotor is stationary, so the rotor speed will be 0, slip will be 1. Under this condition, the rotor experiences maximum slip. So there is slip of maximum slip, that is 1, which results in induced rotor EMF being maximum. So induced EMF will be maximum, hence the current also would be maximum. So that's why it is also sometimes called as large inrush current. Typically, generally 5 to 8 times. Here I have like taken very like bad example, that's why it is more huge, but generally it is 5 to 8 times of the full load current. Okay, so to mitigate this issue, we have like all this can cause problems like significant voltage drop in the supply. If I am taking huge amount of current, so like this is the supply, right? Let's say there is RL here, and let's say the supply is giving some 100 volts. Of course the transmission line will have some its own resistance, very small value, 0.01 ohms, and this will be 0.01 ohms. Okay, very small value. So if the transmission line is 0.01 ohms value, so what I can say is if huge, like if less amount of current flows, like some 10 amps of amount of current flows, then there will be drop of what, approximately it will be 0.1 volts, right? But if the current is huge, let's say current becomes 500 amps of current. If the current is huge, right, what will be, there will be drop of 5 volts. So drop is huge across the transmission line. So in the output, the voltage I will get is 95 volts. So that is not desirable, right? Because the machine was rated at 100 volts. So if the voltage reduces, flux, I mean the flux will reduce, because we know that flux is proportional to V by F. Okay. So these are the problems basically that we will face, and of course other equipments are connected, right? All those equipments are rated at 100 volts, but if there is huge current, they will operate in 95 volts. Due to that, there will be problems, right? May overrate or damage the motor windings, because huge current is flowing, huge copper loss will be there. So this is due to the copper loss. I square R can cause disturbances to other connected loads. Okay, so same due to this reason only. Okay, this is whatever we discuss, due to this reason, because voltage will get dropped and it can disturb the other appliances that are connected. So the purpose of starter is to limit the starting current, prevent this voltage dips, protection against faults. So sometimes if there is suddenly huge voltage is coming from the supply, it will protect the motor, okay, like overload. Then, and if I'm operating in like in huge load, so the load is connected, like huge load is connected, it is taking more higher amount of current, that also it will protect. Okay, it will not let higher amount of current pass through. If there is some phase failure, basically one of the phase is short circuited or something, it will prevent that faults. So starter is there to do all these things. Okay, this is the requirement of a starter. Now the types of starting methods, there are many kinds of starting methods, okay, which you will see. Okay, which will, ultimate goal is to reduce the starting current. That is the ultimate goal of all these starters. The ultimate goal will be to reduce the starting current. Sometimes few method is better than the other, it depends on your requirement. So we will use any one of these starters depending on our requirement. So this is the first one, that is direct online starting. In this, right, the starter will be used just to have this protection against overload, phase failure, short circuit. It will not actually reduce the starting current, right? Starting current, it will not do anything. Whatever is the starting current, it will not change it. So starting current in direct online will not change. Starting current will remain same. Then you will say, sir, what is the point? The point is it will help in protection against faults. Okay. And then what's the point, sir? Sir, you are saying it will not change the starting current, but you told starting current is very high. For few motors, right? For few motors, maybe the starting current is not that high. We can calculate that. Maybe the starting current is not that high without any starter. So for those kind of cases, we don't need all these fancy equipments, right? We can save cost. To save cost, we will only use this. Okay, we will not use this kind of things. Okay, this is what we will use. If the starting current, this is generally used where the starting current is low. Okay, otherwise we have to use all this, right, which is known as reduced voltage starting. We will not apply the full voltage, rated voltage, we will reduce the voltage. Okay, so in reduced voltage starting, there is stator resistance starter. It will be similar to a starter of DC machines. For those who have studied DC machines, they will know about this. Okay, almost similar. We will connect resistance on the stator side, so that there is, like, whatever huge current is flowing, there is voltage drop on the stator side, and so full voltage is not getting applied in the rotor side, so the current will be reduced. But there will be power loss in the stator resistance. So kind of a trade-off. Again, auto transformer starting. So instead of initially giving the full voltage, what I can do, we can gradually increase the voltage with the help of auto transformer. So auto transformer can help, because auto transformer means it can change the voltage levels. If I change the voltage levels, the current also will be changed. Then we have star delta starter. So we know that in star, if I am applying 400 volts in the line, in the phase it is 400 by root 3. So the voltage level is reduced. So that is what star delta starter can help us do. Then we have rotor resistance starter. This will be only applicable in I think slip ring, whatever in whichever type of rotor there is provision for addition of resistance. So this kind of method can be used to add the resistance on the rotor side and the current will be reduced. Okay. So let's now discuss the first one, that is the full voltage starting. In here not much analysis is there, just that we are applying the full voltage and we are measuring the currents so that we can compare with the rest of the methods, how much current is reduced in the rest of the methods. Okay, that is what we want to compare. Okay, so here there are few things. We know what is the torque developed. So of course there is friction and windage loss, all those losses are there. Ignoring those losses, I can directly say the torque developed, right? We have already discussed about the power flow of induction motor. Torque developed will be the air gap power divided by the synchronous speed, right? This we have discussed already. So what is the air gap power? So if I bring you the circuit again, right, air gap power is this whole power, right? Now what is the power consumed here totally? So how can I say what is the total power consumed? So if I want to say what is the total power consumed, what I can do is basically I can what equivalently, like initially what was the resistance, it is, if I write this to equivalently, it will be R2 dash divided by S. So it will be R2 dash divided by S. If I want to write them equivalently, so R2 dash divided by S, I'm ignoring the stator resistance for a second and the stator reactance. Okay, only the rotor reactance and the rotor resistance I'm taking into account. Okay, so what will be the air gap power? The air gap power will be basically equals to this 3-phase air gap power will be 3 into I2 square into this R2 dash divided by S. That is what my air gap power is equals to, right? So in full load what will happen, because I want to compare the full load torque and the starting torque and the full load current and the starting current. So basically at full load my I2 will be equals to I2FL, right? That will be my I2FL, or I can directly write this IFL only, that does not make any difference. So what will be my full load air gap power? Full load air gap power will be 3 into I2FL whole square into R2 dash divided by S. Okay, now what will be the torque, full load torque? Full load torque will be this power full load is there, so this will be 3 by omega S into I2FL whole square into R2 dash divided by, okay, sorry, I forgot to write, this will be SFL, right? SFL also will be there. Okay, cannot forget the SFL because slip will be full load. So at full load the slip also will be SFL. Okay, so now if I want to compare, right, at starting what will happen? At starting, the slip will be 1, right? Starting current will be I2 will be equals to I2 starting, right? Sometimes in few books they will write this as I2 SC, where SC means the starting current. That's it. Okay, SC basically means the starting current. Okay, so if I want to compare like what is the torque difference and all those things, right? I can directly compare. So what will be the starting torque? Starting torque will be again 3 by omega s into PG starting. So PG starting will be basically this time I2 SC whole square into R2 dash. S will not be there because S is 1, right? It will automatically be nullified because S is 1, right? So the ratio of the starting torque to full load torque equals to 3 by omega s will be cancelled out. So it will be I2 starting current divided by I2 full load current whole square into so this will be SFL. Okay, so this is the ratio with online starting, direct online starting. So we will compare this ratio with all the others. How much am I able to improve it? Okay, so this is the ratio with direct online starting. Okay, so yeah, I hope you have understood this point. Now like this is without any external resistance, nothing we have added till now, just basic thing we have done, right? Now we will compare. Now the next like this is the thing that we are doing, full voltage starting, where direct motor is directly connected to the supply to a starter. That includes over only, it will include over voltage and short circuit like fault. That I am not discussing how it will do it. Okay, there are a few magnets and stuff, we are not discussing that. Mainly we are concerned about the starting portion. Okay, so it is suitable only when the supply system is strong enough to tolerate high starting currents without significant voltage drop. It is used in small motors where the starting current may not go very high. Because the rated current is already very low, so supply can handle it. So if the rated current is 10 amperes, then the starting current will be 80 amperes. Maybe the supply is able to handle it, right? So for lower rating motors, we can handle it, but for higher rating motors this will not be enough. We have to use other means, that is reduced voltage starting. We will discuss about that. Okay, so like what is the advantage? It's simple and economical. We don't have to add any extra circuitry. That's why it is simple, and we don't have to bear any extra cost. And full load starting torque is available. So as initially, right, why is the current very high? Because the torque that it needs to produce initially needs to be very high, because the motor is not rotating. So motor needs to start rotating, so that's why the torque initially is very high. So at starting we are getting full torque, if you see here, because I2SC will be very high compared to I2FL. But in other methods the starting torque may be lower. So what will happen if the starting torque is lower? So let's say if I have a motor here, right? If I have a motor here, and let's say the load torque is 20 Newton meter, right, in this direction. So of course the motor will generate a torque in this direction, opposite direction, to nullify this torque and for the motor to start rotating, because the motor must start rotating, right? How it will start rotating? The developed torque must be greater than the load torque. So that's why initially the starting torque will be much higher. So for the motor to rotate, so let's say it is 40 Newton meter. So now as soon as the motor will start rotating, the current will reduce. So the developed torque will reduce. Let's say it will reduce to 30 Newton meter, right? Then it will reduce to 20 Newton meter, and at 20 Newton meter it will stabilize. Basically the both of them will be stabilized basically, because the speed will be constant, because the load torque and developed torque will be equal. So the overall torque will be 0, so speed will be constant, there will not be any acceleration. So that is the thing. So here this is fine, because starting torque I am getting very high value. But in other methods, you will see, we will compare this, the starting torque will reduce. If the starting torque reduces to 30 Newton meter, then also it is fine, no problem. But if the starting torque reduces to 19 Newton meter, what will be the problem? If the starting torque reduces to 19 Newton meter, there is not enough torque for the motor to rotate in this direction, right? Because load torque itself is 20 Newton meter. So motor will simply not rotate. Motor will simply not rotate. Just like, I'll give you an example. In your class, right, there will be a very heavy person, okay, very fatty person, right? And if you want to push that guy, right, you will have to produce enough force to push that guy. I am not that strong. I am very lean and stuff, right? I will not be able to push that. So I am not able to generate that amount of starting torque. So that guy will not move. That fatty guy will not move, right? So basically, I am here, okay, very lean guy, okay, and that fatty guy is here, right? Fatty guy. So I am trying to push this guy, but my power is not that much high, right? My torque is not that high. So this guy will not move because the weight of this guy is very high. Let's say 100 kgs. My weight is only 40 kgs, not 40, 50 kgs. Okay, my weight is maybe 50 kgs. Okay, so if my weight is only 50 kgs, I'm not able to push this guy. Generally, that is a trend that if the weight is higher, that person is more stronger, right? So again, now if some other person comes up, right? Okay, not a girl, boy only. Okay, so let's say his weight is 70 kg. If that guy pushes this guy, right, then this guy will be able to move. Then there is no problem, right? So you have to produce that initial torque, enough initial torque to move this guy. Same here, right? I have to produce that initial torque to move the motor, else the motor will be simply locked. So here, if the torque is lower, if the starting torque is less than full load torque, then the motor will simply lock. Okay, motor will simply lock. That's it. Okay, so these are the things we will discuss slowly. Disadvantage: high starting torque. It is not, sorry, high starting current. It is not changing the current at all. Not suitable for weak supply systems, right? If supply system is weak, if huge current will flow, then the other equipments can get damaged. So that is a disadvantage. Now that's why for those kind of things, we will come to the next kind of starter. In this starter, what we'll do, we'll connect before giving the like supply here, right? We will give the supply here only, same position, but we will connect few resistance, stator resistance, and due to those stator resistance, what will happen? The current will be reduced. Okay, the current will be reduced. So let's assume that if there was no uh, there was no resistance connected, what was the impedance of the coils? Impedance of the coils, let's say, is ZSC, the starting current default impedance. When no impedance of coils, these are all the impedance of coils, right? Okay, these are all the impedance of coils. Now what we can do is, now am I connecting a resistance? So if I am connecting a resistance, what will happen? Basically, this voltage, right, per phase equivalent, if I want to draw this thing, per phase equivalent, there is this resistance, correct? Then I have this coil whose impedance is ZSC. So what will happen? Basically, I am applying the voltage here, but actually this voltage will be some V dash, and V dash, there will be some voltage division, right? So V dash will be equals to what? Some X factor, X will be less than obviously X into V, because there will be some voltage division, some voltage will be dropped here and rest of the voltage will come here. So V dash, like basically my X will be between 0 to 1. Okay, X will be between 0 to 1. That is what my V dash will be equals to. Okay, so now what we can discuss is that Yeah, so what will happen to the starting current? So what is the starting current now? So ZSC was the starting current with direct online. So whenever I write ISC ZSC, right? ISC ZSC, whatever I write, so this I can write as TSC. Whatever parameters I am comparing, these are all with DOL. So whenever there is SC, right? Starting SC. So those are with respect to DOL, okay? Because I want to compare with respect to DOL. So what will be the starting current in this case? The starting current in this case will be what? What is the voltage? V dash. What is V dash? X into V. So it will be X into V divided by ZSC. Okay, that is what my starting current is. So so X will be, so X is whatever value, some ratio, okay. So basically what happens, what is V upon ZSC? So V upon ZSC was basically when there was no resistance connected. So this, right, what is starting current? Starting current will be V upon ZSC when there was no resistance connected. So basically my starting current will reduce by a factor of X, right? Because X is between 0 to 1. So starting current will be reduced by a factor of Z in case of a stator resistance starting. Okay, that is what you have to understand. Don't have to mug up anything. Understand conceptually what is happening. So starting current reduces by a factor of X. Okay, now what will happen to the other like starting torque? So what is my starting torque proportional to? Again, my TSC was what? In case of direct online starting, in case of direct online starting, TSC was 3 upon omega s, right, into ISC whole square into R2 dash, right. What will be the starting torque here in this case? The starting torque here will be simply 3 upon omega s, everything else is same, right, into I starting whole square into R2 dash. So basically if I want to take the ratio, how much is the starting torque getting reduced? So T starting divided by TSC will be basically ISC. What is IST? IST is this, right? X into ISC. So basically it will be X square into ISC whole square. ISC, all other are same. So all everything else will be cancelled. Only X square will remain. So this is another important thing. Don't have to mug up this, but you have to understand this, what is happening, that the starting torque is getting reduced by a factor of X square. Now tell me, is that desirable or not desirable? This is not desirable, right? I told you, right, with example. So this is absolutely kind of not desirable, right? Not desirable. Also one more thing is there, that this whatever external resistance or external we are connecting, whatever current is flowing right now, starting current, right, there is some loss in the external resistance, that is I, like 3 times, because it is per phase, so it will be 3 times the external current, sorry, the starting current. Slowly the current will reduce, but initially there will be huge losses, right, are external. So this thing also is undesirable, right, undesirable. So these are few drawbacks of this. So although we are able to reduce the starting current by a factor of X, right, this is desirable, but this is not desirable, this is also not desirable, right. So those are the things that is written over here. The starting torque reduces, so also it results in power loss. So it, again, this will be used in small motors where a moderate reduction in the starting current is acceptable, and starting torque also will reduce, but that will be manageable, that we can manage. Still it will be higher than the load torque. Okay, so now let's discuss regarding the auto transformer starting. So in auto transformer starting, what we will do, is I will not use resistance. I will directly connect here a voltage source. I will directly reduce the voltage. Previously, what was happening in the previous case, I had a resistance and then I had the winding. So I was applying a V voltage here. I was getting a V dash voltage that was equals to X into V. But now what I am doing with the help of auto transformer, I am directly reducing the voltage. So directly I am applying some V dash voltage over here, that is equals to X into V, and that is directly coming here across the coils. So this time there is no voltage division, because auto transformer, what it will do, it will conserve the energy and power, that we know. So there is no dissipation in the power loss. That is the advantage of this particular thing. That is the advantage of this case, right? So what is happening, the voltage is getting reduced by X into V. So because like here I have auto transformer, correct? So I'm just reducing the voltage, voltage I'm reducing by X into V. Okay, what about the this impedance is still there. Okay, that is ZSC. Impedance is still there, that is ZSC. Okay, so how much actually is the current getting reduced? That is what we have to identify. How much is the current is getting reduced? So what we can do, we can use the balance equation, right? So here I am applying, actually how much voltage I am applying, I am actually applying here V1 voltage only, right? I am actually applying here V1 voltage only in the primary side, right? But here I am getting voltage XV, here current is IA1, okay, but here how much current is going, as I am applying XV amount of voltage, how much current it is taking? Still it will take how much? X into ISC. Why? Because the voltage here, like if I draw the equivalent circuit, I have the coil per phase equivalent, I am applying a voltage XB, right? What will be the current? Current I starting current will be what? This impedance is ZSC, so it will be XV divided by ZSC. So it is basically X into ISC, right? So this is X into ISC, this is some current IA1. But I want to see how much current reduction there is in the supply side, because whatever we're comparing with respect to the supply side, because here also here this supply current and this current, coil current was same, but here they are different because auto transformer is there. So what is happening to the supply side? So to the supply side, I will use the KVA balance equation. So KVA of the primary will be equals to KVA of the secondary. Okay, so V1 into this current I1 that I want to measure, actually how much is their reduction, IST, okay, is equals to, in the secondary side the voltage is what of the auto transformer, X into V, right? Secondary side voltage is X into V. What is the current? Current is X into ISC. X into ISC. This is the current, this is the voltage. So from here I can say what is the like V1. V1 is V only, right? Basically I am just reducing the voltage by a factor of X. So V1 is V only. So from here I can get the equation of starting current in the primary side, that is X square into ISC. So now the advantage of this, there is higher current reduction. In the stator resistance, the current was only getting reduced, the supply current was only getting reduced by X into X factor. But here the advantage is the supply current factor of X square. Hence the torque. What is the torque? Torque depends on this current only, right? Whatever is the coil current. So what is the difference of the torque? So again the starting torque divided by the, this will be x square only, this will not change basically because the torque depends on this side, right? I was interested in the supply current because the supply current was higher, so I had to reduce the current. Okay, so if I compare the torque, that will depend on the current on the coils. So what is the current on the coil? In the uh, starting case, in this auto transformer case, what is the current? Current is x into ISC, right? So it will be x into ISC whole square because it is 3 into I2 square into R2. So that's why it will be x square into ISC. So and in the denominator, in the direct online starting, the current was ISC whole square. So ISC whole square will get cancelled, simply x square will be there. So advantage of this is torque is getting reduced by x square, so is the starting current, and there is no power dissipation. So that is the advantage. Disadvantage is we need auto transformer, which is a costly equipment. Okay, that is the disadvantage. So the starting current also will be reduced by x square. Okay, in the supply side. So this will happen in the motor side, stator side. The current will be reduced by a factor of x in the stator side. In the supply side, the current will be reduced by a factor of x square. Okay, on the on the supply side. Okay, so this has better efficiency because there is no power loss in the external resistance. Starting torque is higher than the start delta. We will see what happens in start delta method. Here the starting torque will be higher. We will see, compare it. Suitable for large, if the power rating is larger, so the reduction is current is also very good, right? X square. So if the current is very larger, it will be better, right? It will be better for us if I use auto transformer. We can compare as well. If you want to compare, you can compare as well. That let's take a few numbers, right? Let's assume that in case of direct online starting, the starting current that was coming, ISC, was coming out to be, let's say, 200 amperes, right? And that starting torque was coming out to be, let's say, 50 Newton meters. Okay, now if in case of a stator resistance method, what is the like, let's take a few numbers. Let's assume that x will be 0.7. I'm not reducing by far, x is 0.7. So if x is 0.7, then how much does the starting current reduce? It will be x into ISC. So 0.7 into 200, it will be 140 amperes, right? What will be the reduction in starting torque? It will be x square into the torque, that is 0.49 into the starting torque in the direct online case. So it will be around 25 Newton meters. Okay, let's check the same, and remember here there will be power loss as well, right? In auto transformer, if I check in auto transformer, what is x? X is equals to again, see, x will be same only 0.7. What will be the starting current now? Starting current will reduce by x square. I'm talking about the supply side. So in the supply side, it will reduce by x square, so it will become half. So it will be 100 amperes. So will the starting torque. It will also become half, 25. So even though there is reduction in starting torque by a good amount, the starting current is also getting reduced. So there is, that is the good thing about this, right? About the auto transformer starter. Also for higher currents, right? 200 amperes may not be suitable in supply. So we have to anyways use the auto transformer. Okay, so let's now discuss about the other method, that is the star delta starting. So before explaining all this, I want to write down few equations, right? So in this method, what we will do, we will start our motor using the star connection. Okay, the supply will be star connected. By default our motor will be in delta. By default our motor will be in delta connection, but I will give star connection. Okay, this is wrong actually. This is kind of wrong. This is not correct, right? So basically what we will do, by default here, right, in this method can only be used if the motor is delta connected. Okay, so I will write here method can only be used if motor is delta connected. Okay, so if motor is delta connected, then initially at starting what I'll do, I'll connect them in star. So how will I connect them in star? So from the supply side itself, I will like change the connections. Basically they're like these wires, right, these windings. I will change the connections of these windings. Somehow there will be connections. So in the starting they will be connected in star. Okay, these coils will be connected in star. How we connect things in star? So what we do is, although the windings are in delta, right, what we can do, we can connect them in star. How? So we'll connect this point to here, and this point to here, and this point can be connected to this point, right? And all of them will have a common connection. So common point will be this one. Okay, so this is how we can connect them in star, although this does not look that great. Okay, how will I pictorially represent it in a better manner? So basically what I mean, right, basically in star what happens, in star how are the windings connected? So basically in star, if you know, there is one common point and rest of the 3 points goes to the supply, right? That is what I am trying to replicate over here. So there will be a common point, that will be, so these points will go to supply, rest other points can be common. Okay, that's it. So these points are common and rest are supply basically. So internally I will change the connections somehow so that it becomes star connected, but by default motor is delta connected only. Okay, by default motor is delta connected. During normal operating condition it will be delta connected. Okay, during starting I will just change the connections, change the wire to make it star connected. Why so? So let's assume that if the motor is started with DOL starter. Okay, DOL starter meaning there is no like star delta starter. So basically by default the motor is delta connected, we will start with delta connected only. So in delta what happens, the voltage does not change. So if I am applying some voltage V over here, the same voltage will be reflected in the coils, and the coil impedance is ZSC. Okay, so the current, what will be the current, what will be the coil current, right? What will be the coil current in delta? Coil current in delta, right, this is the coil current, I am talking about the coil current in delta, is equals to V voltage upon the coil impedance ZSC, right? So this is what, this is simply ISC, right, the starting current normal delta operation. But remember this is delta connected. In the supply side what I am seeing, in delta connection what happens, that in the supply side the line current is root 3 times the phase current. So the starting current in line, this is the supply side of delta line current, this will be just starting delta, okay, this will be equals to root 3 times ISC, the normal operation, okay. Now this is fixed, this is with respect to what I will compare, because I mainly am comparing the supply current, okay. Now let's discuss about the things that if we started using star connection, right, instead of delta. Now this is the full load condition, like if I did not have any star delta starter, then this would have been the supply current, right. If I would have started with a star connection, what would have happened? If I would have started with a star connection, so if star delta starter is used, if star delta starter is used, then what will happen? If star delta starter is used, then I can directly say that I will just redraw the diagram, right, the coils diagram, that will be easier for us to understand. I am just rearranging the wire connections to make it star connected. So now if I am applying a voltage V across the line, what is the voltage that I will receive across the phase? The voltage that I will receive across the phase will be V by root 3. Now remember, please don't compare it with the direct online starting. In that case, by default, my windings were star connected only. That's why I was not comparing this voltage, reducing the voltage there. Okay, that's why. Here, as the by default the windings are delta connected, so by default the voltage will be V. Okay, so those things have changed. So here I am receiving V by root 3 voltage. So what will be the current? I starting, right? In star, the starting phase current and the line current are same. It will be basically V by root 3 divided by ZSC, right? So which is V divided by root 3 into ZSC. Okay, so this is V divided by root 3 into ZSC. So now what I can say that what is the starting current, because this is the line current only in star, it is V divided by root 3 into ZSC. That is what the V divided by ZSC is what ISC. So ISC divided by root 3, right? And from here, if I want to directly compare what is my ISC from this equation, what is my ISC? ISC is equals to I starting of delta divided by root 3. So ISC is I starting delta divided by root 3. So basically what is happening, compared to the delta, the current is getting reduced by 1/3. So my I starting of delta is I starting of star is I starting of delta divided by 3. So current is getting reduced by 1/3, right? Supply current is getting reduced by 1/3. Now what about the torque compared to the delta side? I'm talking about the delta side, I mean compared to the delta connection, supply connection, right? What about the torque? So for torque I can directly compare the this like this is one equation, right? Another equation is this. Okay, don't forget this, there is many confusion in this, so that's why I have written everything crystal clear. What about the starting torque compared to direct online starting, right? So starting torque in direct online starting, what was the starting torque? It is basically the ISC current was flowing, right? The starting in the coil, what current was flowing? ISC. So due to that, what torque I get? TSC, right? Basically TST divided by TSC, right? In direct online starting, it will be V, sorry, 3 upon omega s. I'm talking about the delta connection. It will be what? ISTY. Now what is the ISTY? So in case of In case of delta, in case of star, it is ISC divided by root 3. ISC divided by root 3, right? So basically, it is V divided by root 3 ISC. Sorry, it is V divided by root 3 into ZSC, right? So basically, my current is getting reduced by root 3 times compared to the direct online. So this I have compared to the delta connection. This I am comparing to the direct online. Okay. So that's why it becomes 1/3, because by default my motor will operate in delta connection. That's why we're comparing it with respect to delta. Okay. That's why we're comparing it with respect to delta, the currents that I'm talking about. So here this will be TST divided by TSC into I SC whole square, sorry, IST whole square. IST whole square compared to ISC is this ISC by root 3, right? I will write that into R2 divided by into ISC whole square into R2. So what is IST? IST is ISC divided by root 3. So this will be TSC will be equals to ISC divided by root 3 divided by ISC whole square. Other things will get cancelled. So the torque also basically into TSC is here. Torque also becomes 1/3 compared to the direct online starter. Okay, compared to direct online, torque will become 1/3. Same you can do it here as well, because why I had to do this? Because I wanted to compare the line current. In delta the line current was different, but remember the starting current of coil is still ISC, right? Starting current of coil is still ISC. So starting torque is still TSC here, right? But as I'm comparing the line currents, here I'm comparing, this is the supply current, that's why I have to convert it into delta. That is the only reason. That's where I can say that the line current has reduced by 1/3, okay, and the torque also has reduced by 1/3, because the current is still ISC here, and ISC current is V by ZSC, and in this case the current will be V by root 3 ZSC. So if I am squaring it, so the the torque will be 1/3. So similar kind of things we are seeing in auto transformer and in star delta, just we don't need a auto transformer here. That is the advantage. Okay. So here the starting current becomes 1 by root 3 of the direct online starter if this is for the coil side or the stator side. But on the supply side, the starting current will be 3 of the delta connection. This is on the supply side. Okay. So here motors are generally used in the range of, this is mid range. If you are using mid range, then we will use star delta, because there is no flexibility, right? In auto transformer we have the flexibility. If I want higher range, because here what is the maximum, like what is the equivalent of this auto transformer? So in auto transformer what used to happen, the current used to get reduced by x square. So here it is getting reduced by 1/3. So basically my x, what kind of tapping I will need? 1 by root 3. What is 1 by root 3? It is basically 57.7%. So in auto transformer I need to tap 57.7% to get the same working, same current as star delta. Okay. So yeah, auto transformer starting is analogous to star delta tapping if the tapping is 57.7%. Okay. So yeah, that is what we have discussed over here. So for higher powers we will use auto transformer, because we have flexibility. I can reduce the x further to reduce the starting current, but that the flexibility is not there in star delta. So generally we use in the range of mid range, basically 5 HP to 20 HP motors. Now let's discuss about the rotor resistance starting. So in rotor resistance what we'll do, we'll connect our resistance, external resistance to rotor side. Again one thing, this can only be used in slip ring induction motor, cannot be used in cage induction motor, because there is no provision to connect resistance electrically on the rotor side. So can only be used in slip ring okay, this can only be used in slip ring induction motor. So what is the starting current? starting current basically, in this case, what is the formula for starting current? If you remember, it was roughly equals to R2 dash by S whole square. Sorry, starting current S was not there. R2 dash whole square plus X2 whole square whole under root, right? Because I was ignoring the stator resistance. Now, what is R2 dash? What is R2 dash? R2 dash is basically this rotor resistance, right? So R2 dash, if I change R2 dash to R2 dash plus R external, then what will happen? Then basically your R2 dash will increase. If R2 dash increases, the starting current reduces. So like this we can change it, but remember, if you are changing R2 dash, few things will change. Do you remember the torque speed characteristics? So if you remember, the torque speed characteristics was somewhat like this. This is the torque, this is the speed. So this was a slip, basically torque slip characteristics, slip or speed, whatever you want to say, and it was somewhat like this, right? So I had a torque speed, this was torque speed only actually. So I had a maximum torque here, and do you remember the point at which the maximum torque occurs, slip at which the maximum torque occurs? What was the formula for that? Okay, we discussed this, right? I think previous to previous lecture. So slip SM is equals to R2 dash by X2, right? So if I'm changing my R2 dash, then the point at which the maximum torque occurs, that is also changing, right? So just be careful regarding that. Although, yeah, this is very good actually, but still there will be some power loss in the external resistance, but this also is getting changed. So the characteristics of the motor also will change. So just be careful regarding that. So if I keep on adding external resistance, the torque slip characteristics will shift. So I am increasing my R2 dash. So if I am increasing my R2 dash, right, what is happening? My slip is increasing, correct? So if my slip is increasing, that means basically my graph will shift backwards. Why? If slip increases, that means my slip is increasing, right? If slip is increasing, my NR will reduce. That is the thing, right? Because slip is what? Slip is NS minus NR divided by NS. So slip is increasing. So if slip is increasing, then this difference will increase. If this difference increases, that means this is constant, so this has to reduce. So NR reduces. If NR reduces, I will go backwards. So basically what will happen, the graph will shift backwards. So if I plot this, right, if I plot this here, omega, if you guys remember, there was an equation for the maximum torque. It's like not important, but for this graph I want to say that it actually, the maximum torque did not depend on the, like approximately it did not depend on the rotor resistance, it was mainly depending on the rotor reactance. So it is 2x2 dash. Okay, so roughly it is constant. If I am changing my rotor resistance, the maximum torque does not change. So if initially my graph was somewhat like this is my maximum torque, right? This is my maximum slip, right? Initial slip. And maximum torque, let's say Tm1, this will not change. So although the graph will shift on the backwards, because the slip at which maximum torque happens is getting increase. So if slip is increasing, speed will reduce. So basically the graph will shift backwards. So if I shift the graph backwards, it will be somewhat like this. Okay, if I shift it more backwards, okay, I don't have space, so I'll shift it in the between, somewhat like this. So what is happening is here there is no external resistance. R external, this is, let's say R external 0, this let's say is R external 1, and this let's say is R external 2. Okay, so basically what I can comment is R external two will be greater than R external. As I will keep on increasing the external resistance, the graph will shift backwards. So there will be increase in the starting torque. There will not be actually decrease in the starting torque. The starting torque will increase further. So it increases the starting torque. That is the advantage. If I add external resistance, we will get an increased starting torque, but only the maximum, the speed at which maximum torque happens, that will change. So that is the disadvantage. Okay, so we reduce the starting current, we increase the starting torque. Both these things are actually desirable, right? That is what we discuss. Both these things are desirable, but the problem is it will shift the torque slip curve. So this is kind of, we don't want this, right? Maybe we thought of designing our system that it will operate in this speed at maximum torque, but it is not operating. That is the disadvantage. Okay, so higher rotor resistance, higher starting torque, the current will reduce, but the starting torque will increase. Okay, so as the speed increases, the external resistance are gradually cut out. So what we do, actually what we do is, initially we give external resistance, right, to reduce the current. Slowly, gradually we will remove the external resistance so that our torque speed curve does not change in full load. So that is the basic procedure. Okay, but here again there are losses in the rotor, right? External resistance. What is the losses? 3 into I2 square into R external. That is the disadvantage of this method. Okay, so what are the advantage? Advantage is smooth acceleration with high torque. So we are getting high starting torque and we are able to accelerate smoothly. So controlled, we are able to control the current, but it is more expensive because we have to connect, and complex because we have to connect on the rotor side, and rotor is rotating, remember. So expensive, and there will be wear and tear. Okay, as we are connecting on the rotor side, as there are moving parts, there will be maintenance because the resistance will get wear and tear, right? So brushes and slip rings will require maintenance. Okay, that is the disadvantage of this. So this is the summary table. Basically, you can go through this. Okay, so in case of star delta, the voltage gets reduced by 1/3 because we are connecting it in star. The current reduction is 1/3. This is for the supply side, supply current. Okay, supply current. Okay, the voltage in auto transformer is reduced by x, and current will be reduced by x square. Okay, and torque also will be reduced by x square. Okay, and now this is used for higher power rating. This is used for medium power rating, star delta. Okay, and rotor resistance is used in slip ring motors, and torque reduction will be not high. Torque reduction will not happen, right? Sorry, torque reduction will not happen. Torque will increase. This is wrong actually. Torque increases. The starting torque increases instead of reducing, right? So I will write here. Okay, starting torque increases. Voltage at start we will get full as the rotor voltage, then we will control it. Current reduction will be controlled depending on the external resistance. Okay, so these are the different methods, and these are the application ranges where we will be using it. Okay, I might should actually, this is fine, it's fine. I hope you will be able to understand, like this is the gap basically. So let's do few questions and to understand our, like, make our understanding even better. Okay, the starting line current of a 415 volt 3-phase delta connected induction motor is 120 ampere. So the line current of a 415 volt delta connected supply is 120 amperes. Okay, so in the coil side, what will be the current in the coil side? So I know coil side I will get rated current because I am providing, if you remember, the starting line current of a, okay, 3-phase delta is 1 when okay. So basically of a delta connected, so here, right, they have not mentioned anything, right? Whether they are using a star delta connection or anything. If they have not mentioned anything, I will assume it's a direct online starting. So it's a very simple question. They have told that it is a delta connected induction motor, and in rated voltage it takes 120 amperes of current. Okay, 120 amperes of current. Okay, so then what I can say, line current is 120, so starting current is 120 divided by root 3 in the phase. Sorry, this is, they have told us the line current, sorry, they have told us the line current, this is not the phase current, right? Phase current will be divided by root 3 at a rated voltage, that is 415 volts. Okay, V is 415 volts. Now they are telling me, tell me when I am applying, what is the starting line current when I am reducing the voltage to 110 volts. So if I am reducing the voltage to 110 volt, what will happen? So what was the starting ISC? ISC was V upon ZSC, right? So in the second case, ZSC will not change, so it will be directly proportional to the voltage. So it will be V dash upon V into the previous starting current. So it was V dash upon V. V dash is 110 volt, and remember in delta, line and phase voltages are same, so they do not change. So 110 divided by this is 415, okay, into 120 is there. So what is the current here? If I want to write down the current, this will be 110 divided by 415 into 120, so 31.8 amperes. 31.8 amperes will be the, remember it will be the, sorry, not 120, so 120 divided by root 3, right? 120 divided by root 3, this is the phase current. Now I have to find out the line current. So what is the line current? Because they have asked me what is the starting line current. So in delta, line and phase current are different, right? So line current will be simply root 3 times the phase current in delta. So it will be 31.8 amperes. So 31.8 amperes will be your answer for this question. So in this, right, they have not mentioned what kind of starter they have used. So if nothing is mentioned, we'll assume that we are using direct online starter. Very simple, no analysis needed. Okay, now let's solve the next one. So it is a common data question. So here, a 3-phase squirrel cage induction motor has a starting current of 7 times the full load current. So IST is 7 times the full load current, IFL. I guess it is telling in normal direct online connection, and the full load slip SFL is 5%, that is 0.05. Okay, if an auto transformer is used for reduced voltage starting to provide 1.5 unit per unit starting torque. Okay, so what are they telling me? If the auto transformer is used to reduce the voltage to provide 1.5 per unit starting torque. So basically my starting torque than the normal condition, it will be 1.5. Okay, sorry, 1.5 per unit starting torque. The percentage of the, what are they telling? If the auto transformer is reduced voltage to provide 1.5 per unit starting torque. Okay. So basically starting torque is 1.5 pu. Do you understand what it means? It basically means that starting torque is 1.5 pu. What is pu? Pu is the value, starting torque value upon the starting torque. Pu will be starting torque value upon the full load, right, rated condition torque. So this is 1.5 basically. So from here I can directly deduce that they are telling me that the starting torque will become 1.5 times the full load torque. Now in direct online starter, what happens? In direct online starter, what happens? So in direct online starter, what is the ratio? So what is the ratio of the starting torque upon the full load torque? That is what I want to see, right? In direct case. So it will be what? If you remember, it was the current whole square into the full load slip, or you can directly write this down. Okay, so it is 3 into 3 by omega s into I square into R2 divided by S, current whole square into resistance, right? So everything else will be same, just the current and the resistance is changing. Even in resistance, R2 divided by S, S is changing, right? R2 divided by S. So in the first case, in the first starting case, S is 1, slip is 1. In the full load case, slip is SFL. So basically what will happen? This will be I SC whole square into R2 divided by SC, that is 1 only, divided by I FL whole square into R2 divided by SFL. Okay, so basically R2 R2 will get cancelled, only what will be left? TSC by TFL will be equals to ISC whole square divided by IFL. So ISC whole square divided by IFL, I already know what is the ratio, it is 1 by 7, right? So ISC 7 times, so it will be ISC divided by IFL whole square into SFL. So this is equals to ISC is 7 times IFL, so 7 whole square into SFL is 0.05. So 49 into 0.05, so roughly it will become 2.45. Now what happens in, like they are asking me what is the tapping that I need to provide, okay, to get this ratio. Currently the ratio is this, right? 2.45. I have to get this ratio. Do remember one thing, what we used to do? So if you remember, in auto transformer we compared the starting torque with auto transformer, without auto transformer, that is direct online starting. It was coming out to be proportional, x square, right? The reduction in torque was coming out to be x square. The reduction in starting torque was coming out to be x square. So from here I can directly take out the ratio. So if I take from this equation 1, so this is my equation 1, T starting upon T full load, because full load torque will not change. If I take this ratio and this ratio, basically the value will be 1.5 divided by 2.45. This will be basically x square. Okay, right? Yeah, correct. So if I am taking the ratio, this will be simply x square. So basically from here I can directly say what is my x into 1.5 whole under root. So this will be 0.782. So this much amount of tapping I need to provide. So 78.25%, 78.25% is C. Okay, C is the answer for this particular question. Now let's move on to the next part of this question. Okay, so if star delta starter is used to start this induction motor, the per unit starting torque will be, what will be the per unit starting torque? So it's very simple, right? If star delta starter is used instead, what do you remember about star delta starter? So in star delta starter, the starting torque is 1/3 of the torque that was produced by the direct online starter. So TST upon TSC is 1/3, and already I have this equation, TSC upon TFL, right? It is what? It is basically 2.145. 2 point sorry 2 point, what was it, 2.45, right? Sorry, 2.45. They are asking me what is the per unit torque, per unit starting torque. What is the per unit starting torque? How do I find out the per unit starting torque? It is TST by TFL, that will be the TST PU, right? Per unit we have already discussed in the first chapter itself. So from here I can directly say that if I multiply these two equations, if I multiply, what will cancel out? TSC will cancel out. It will be TST upon TFL. So 1/3 into 2.45. So my TST PU will be 1/3 into 2.45. So it will be basically 67. Okay, so your value will be option B, 0.8167. Okay, this will be the answer for the second part. Let's now read the third part. Very simple, right? I had just had to find out the per unit, so that's why I multiplied the two equations. The starting torque of if a starting torque of 0.5 pu is required, then the per unit starting current should be, okay, so then what will be the per unit starting current? That is what they are asking. Okay, Now if they have mentioned that, if they have mentioned nothing, right, what kind of starter I am using, I will assume again direct online starter. Okay, so in direct online starter we'll compare, right, like they're asking me what is the I starting current per unit. How do I find out the I starting current per unit? It will be basically I starting pu will be equals to ISC, the actual value, upon the full load current. Now they are asking me the starting torque is 0.5 pu, so that means IST or SC, nothing is mentioned, so it is direct online only. Pu is equals to 0.5, that is equals to what? That is equals to TSC actual upon T full load. Okay, so T full load is what? It is 3 upon omega s into I full load whole square into R2 upon S full load. Right? Again, this is same ratios. This ratio we already know. It is simply ISC whole square divided by IFL whole square into SFL. Right? This value will be basically, it will come out to be ISC divided by IFL whole square into SFL. Now, what is this quantity? Isn't this what I want? Isn't this what I want? So basically, they are asking me this value. So this value ISCPU whole square is equals to, just give me 1 second. Yeah, this is working. ISCPU whole square is equals to this TSCPU divided by TSCPU divided by SFL, right? So I will take the under root basically. ISCPU, what is TSCPU? 0.5 divided by SFL. SFL is what? 0.05. If I remember, it is 0.05. Whole under root. Okay, so it will be under root 10. So it will be equals to 1.63 pu. So this will be the answer for the third part. 3.163. So 3.163 is in present in the option C. So option C will be the correct answer for this particular question. So these kind of questions generally come. So let's solve this next question. So few more questions are left. So you guys can try. So few questions I was doing. So you guys can try out this question. This question you can try out. Okay, pause the video and try it out. This question also you can try it out. Okay, and yeah, these two questions you guys can try. And now I will solve. Okay, so a three-phase four-pole 400 volt 50 hertz. Okay, this information is given. So voltage is 400 volt and it is pole is 4. This information is not required actually. Circuit parameters are this: R1 is 1 ohm, R2 dash, so I will not write this, already it is written here very well. Using approximate equivalent model, calculate the starting torque when the motor is started using direct online. So they are asking me to calculate the approximate torque, right? So what is the approximate torque? So if you remember the, like basically the approximate equivalent model, so this was simply R1 plus, because R1 is given, I will include R1. If R1 was not given, I would have excluded R1. Okay, so it will be R1 plus R2 dash, and this will be J x1 plus x2 dash, and here I will have the load connected, like this is the load only, because R2 dash is the overall thing, right? Here I will not have anything. Basically, you remember, right? Overall resistance is R1 plus R2, because this was overall R2 dash only. If I had added those things, I hope you remember the model. And here I had XM, but I don't need XM actually. I can ignore XM because I'm applying the voltage over here, so I can ignore XM. Okay. So basically, they are asking me what is the starting torque using direct online starter. Very simple, right? So what is the starting torque formula? It is 3 upon omega s into I starting whole square into R2 into R2 only, into R2 dash only, right? Because whatever power, that power should be gone through the R2 dash, due to which I am getting the air gap power, right, not through R1. So I have to find out the starting current. R2 dash I already know. So starting current IST will be equals to V voltage upon voltage is, remember this is the line voltage and it is star connected. So phase voltage will be what? 400 divided by root 3. Don't mess this up. Phase voltage will be 400 by divided by root 3 because it is star connected. Okay, divided by whole under root R1 plus R2 whole square, right? R1 plus R2, R1 is 0.5 plus R2 is 1 whole square plus x1 plus x2. So x1 x2 both are 1.2 only whole square whole under root. This is the starting current. So if I calculate this value, 1.5 whole square plus 1.2 whole square whole under root. So this 1.92 into root 3. So this actually comes out to be 3.327 400. So this will be 1, okay, root 3 is also, okay, root 3 is already included. So 120 amperes around. So current comes out to be 120 amperes. Now we have to calculate the starting torque. So your starting torque will be 3 upon omega s. What is omega s? Omega is 2 pi ns. Ns is how much? Ns I don't know. Ns is basically, okay, it is 2 pi f only, right? 2 pi into f. So 50. That is the frequency. Am I correct here? 2 pi omega s is, no, this is mechanical, right? It is mechanical. Don't mess this up. This is mechanical. So here I have to multiply. So instead of doing it, what is omega s? Omega is simply 2 pi ns divided by 60. What is ns? Ns is 120 f. It is mechanical. All these are mechanical parameters, right? 120 f by p into 60. So here what happens? This will get cancelled. This will be 2. So it will be basically 4 pi f by p. So this I can change by 4 pi f by p into whatever the starting current, that is 120 whole square, into the resistance. Resistance is R2 dash, that is 0.5. Okay. So from here this will be 3 into pole. Pole, number of poles, we have 4 poles. It is a 4 pole machine. 4 divided by 4 pi into 50 into 120 square into 0.5. So here if I want to calculate this value, this will be whole square divided by 50 divided by pi into 3 into 0.5. So it is coming out to be somewhat 138 Newton meter, which is kind of wrong actually, because the answer should have been, actually this should have been 60, like divide by 2, another divide by 2 should have been there. Somewhere I'm missing it up, huh? Let me quickly calculate these values. So this voltage is this. So if I quickly calculate, it is 400. So 1.5 whole square plus 1.2 whole square whole under root. This is only it, right? So into root 3, then into 400, 120.2 amperes whole square into 0.5, okay, into 3, this comes out 21,600. Now 2 pi, 4 pi, so this will become 2 pi something, right? So divided by 4 into pi into 50 into 4, it's coming 138 only. I don't know. Okay, it's coming 113 only. So I don't know if there's some calculation mistake, because I have done the solution. It was coming out to be some 70 something, I don't know, 63 something. So you guys can, I guess you guys can check it out, but for me the answer is 138 Newton meters. This is the answer. Okay, if there is some mistake, you can let me know in the comments below. Now let's do the next question. So this is the last question basically. So a 3-phase delta connected squirrel cage induction motor draws a starting current of 100 amperes. Okay, when connected directly to a supply of 400 volts. So starting current it is drawing delta, when it is delta connected, it is drawing 100 amperes of starting current, right? When it is delta connected, okay, per phase. Okay, it is saying per phase. Per phase meaning, so it is not supply current, it is the phase current. Okay, so basically starting current is 100 ampere per phase. It is the phase current. They have mentioned it. Okay, the line current during direct online starting. Okay, what will be the line current during direct online starting? Simply, what is the line current? Line current will simply be root 3 times the phase current. Okay, so they have given me the per phase current during direct online starting. No starter is there, I'm directly connecting it. What is the line current? I starting delta line current. What will be the line current? Root 3 times the phase current, because this is my delta connected and they have provided me the result for this connection, right? The phase current. The phase current is here 100 amperes. Okay, so the delta current will be ISC. So this will be root 3 times the ISC, that is 173.2 amperes. So this will be the first part, the line current. Okay, so line current will be 173.2 amperes. Now what they are telling me, the line and phase currents during the star delta starting. What will be the line and phase currents during the star delta starting? Now if I am connecting it in star, what will happen? If I am connecting it in star, then the windings will be changed with this, right? So still I am applying the same voltage, right? Previously whatever voltage I am applying, I was applying the same voltage was going through the coils, so the current was V upon ZSC. But now I am applying the voltage here V, right? Here the voltage is V upon root 3. So the current is what? V upon root 3 into ZSC. So the current, the coil current, right? Line and coil current both are same only. So in star, what is the current? It will be V upon root 3 into ZSC. So previously, what was V upon ZSC? We had already calculated what was, this is ISC, right? This was the current, that is equals to V upon ZSC. So now V upon ZSC I already know is 100. So here it will be 100 upon root 3. So this becomes 100 upon root 3, that is 57.73 amperes. So you are observing that in delta connection, the line current was 173.2 amperes. In star, the line current is 57.73. How much reduction is there? 1/3, right? That is what we derive. So did I tell you to mug up anything? No. I did not tell you to mug anything up. I did not tell you, right? I directly used equations. Have I used any formulas? No formula used. Okay. Every other educator will tell you directly use the formula here. No. I derived the formula because that is required, but I am not using the formula. I am directly solving with basics. Okay. Now in the second case, this is the second answer. In the third case, what they are telling me is they are now using a auto transformer starting. The starting current drawn when using a auto transformer with 70% tapping. So what is the starting current in case of a, so if I am using a auto transformer starter, so auto transformer also has to use a delta connection, right? So by default the transformer is delta connected. Okay, so what I will use an auto transformer now. So if I use an auto transformer, so auto transformer, what it will do, is basically there will be tappings. Okay, so I will get a reduced voltage X into V. So here if I am providing V voltage, right, I will get reduced voltage. Due to the reduced voltage, reduced current will flow. What will be the reduced current? XV by ZSC. This will be the reduced current. So again I can use the, like what they are asking me, the starting current drawn when using auto transformer. So starting line current, if I want to compare, because nothing is mentioned, I will assume it to be the line current only. So this is the line current, right, that I will take. So V into IST will be equals to, the secondary side will be X into V into, this is what, X into V by ZSC. V by ZSC is what? V by ZSC is 100. This we had already done. So it is 100, X into 100 basically, right? So basically V will get cancelled. So I starting will be simply X square into 100. Okay, I know I could have directly written this value, but you would not have understood this, right? That's why I am deriving each and single thing. So you guys don't understand what kind of effort goes into explaining all this, right? So here, because other educators, they will not explain, they will directly write this formula directly. Okay, so this will be, now I know what is the tapping. Tapping is 70%, right? That is 0.7. So 0.7 whole square into 100. So this will be 49 amperes. So the starting line current, this is the line current. Starting line current has now reduced to 49 amperes, even further. Previously it was getting reduced to, like in star delta, it was getting reduced to 57.73. Now it has reduced to 49 amperes. Okay. So this is the line current that it will reduce, right? 49 amperes. Am I correct here? Okay. Primary side. Okay, sorry. One mistake. Oh, sorry. One very small technical mistake I made, that actually when I'm using this balance equation, right? This balance equation is with respect to auto transformer. So in previous case, actually our basically line current and phase current was same, but here it is delta. So I have to compare this current, right? Whatever this current is flowing, this is the current through the auto transformer. Okay, slight technical mistake from my end. This is the current through the auto transformer. Okay, this is not the current. This is the phase current through the auto transformer. So I have to compare the currents of the coil of the auto transformer, right? Sorry about that. So this will be IST phase. Just a small mistake. IST phase. So this will become basically, so the phase current will, this is not line, sorry, this is a phase current. Starting phase current is 49 amperes. So what will be the line current? So whatever they have asked. So starting line current will be root 3 times this. So if I take the root 3, 49 into root 3 is 84.87. Okay, 84.87 amperes. So this will be the answer basically. I just want to clear one thing, that here if I'm comparing the phase, I am comparing the phase currents here also, I should compare the phase currents only, right? So I'm comparing the phase currents here, I'm equating the phase currents, and ultimately this is my starting current. Yeah, so this will be my answer, 84.87. This will be my answer for the question. So that's it basically for this lecture. In the next lecture, we will learn about different speed control techniques of induction motor. I hope you have enjoyed this lecture. If you did, make sure to hit the like button, make sure to comment down below, and I will see you in the next lecture. Until then, happy learning.